Hi there, I want you to meet Erwin Schrödinger because he is the one who explained how the electrons move in an atom as a wave. Remember that. So, therefore, we're going to focus now, as part of our review, about the quantum numbers. So, familiar with this diagram? Remember the SPDF? Yes, those are the different shapes of the orbital. So, what's the connection of that to our lesson? When it comes to quantum numbers, they are used to describe an electron in an orbit or atomic orbital, the region in space with the greatest probability of finding the electron in an atom. In here, the Schrödinger wave equation indicates the region occupied by a given orbital in terms of number one, the size of the orbital, second is all about the shape, and the third, the orbital orientation in space, along with its coordinates, the x, y, and z. So let's have the first one. It's the principal quantum number, and the symbol that we use for that is a small letter n. Again, that's the principal. What is this all about? It is the one that describes the size of the orbitals. Is it small or big? So remember that orbitals, as we take a look or review the Paulus exclusion, the number of electrons it can hold, the maximum number it can hold in a particular orbital. The first orbital that can hold only 2 electrons, if you can still remember that. So the size of the orbital is quite small because it's near the nucleus. Unlike the fourth and the fifth that can hold up to 50 electrons, the size of its orbital is really big or large because it's already far from the nucleus of the atom. So orbitals for which n is equals to 2 is of course larger than those with n is equals to 1. Or we can say that the first orbital is smaller than the second one, vice versa. It indirectly describes the energy of an orbital. So aside from saying about the size of the orbital, it may also describe the energy of this orbital based on the Paulus exclusion, or the number of electrons it can hold per orbital. Remember this, that on the first orbital, this is, which is near the nucleus, the energy increases as the orbital gets far from the nucleus, getting bigger. So under this principal quantum number, because they have opposite charges, electrons are attracted to the nucleus, right? Electron is negative, proton is positive. Therefore, energy must be absorbed to excite an electron from orbital in which electron is close to the nucleus, n is equals to 1, into an orbital further to nucleus. Let's say n is equals to 2. Again, the electron should be excited or must be absorbed, or the energy must be absorbed to excite an electron from the orbital so that we can somehow stop the attraction between the nucleus of the atom and the electrons. Again, the quantum number, or the first one, which is the principal quantum, refers to the size of the orbital. Like n is equals to 1, n is equals to 2, n is equals to 3. N, or small letter n, represents, or this is the symbol that we use to describe the principal quantum. The second is the azimuthal quantum, and the symbol is small letter L. It is known as the angular momentum. It describes the shape of the orbital, the S, P, D, F. S for the spherical or sharp, P for the principal, then we have D for the diffuse, and F for the, say, complex shape. Look at this one. So if that is under S, spherical in shape, the value of azimuthal is 0. If that will be in the P, then the value is 1. And if that is in the D, the value is 2. Always remember that. The third one is called the magnetic quantum number, or small letter m. It describes the special orientation of the electron in a space or the magnetic field. The value of this magnetic quantum depends on the value of the azimuthal and may range from -1 to +1, including 0. So again, the value may range from -1, 0, +1. That is for the magnetic quantum. This is for the P, for the D, and for the F. So remember the sublevels. The S sublevel, the P sublevel, the D sublevel, and the F sublevel. Where did I get the 2, 6, 10, and 13? So in here, remember that in the spherical shape, we only have 2 examples of that. In the P, we have the X, Y, and Z times 2, that is 6. For the D, we have 10, and for the F, we have 14. Let's go back again to the pictures showing it. So we have for the S, this is for the P, for the D, 1, 2, 3, 4, 5 times 2. Then for the F, 1, 2, 3, 4, 5, 6, 7 times 2. The reason why we get a value of 2, 6, 10, and 14. And what about the magnetic values? For the S, 0. For the P, since we got 6 here, -1, 0, +1. For the D sublevel, we have 5. Those are -2, -5, 0, +1, +2. Then for the F sublevel, they are 7 here, namely -3, -2, -1, 0, +1, +2, and +3. Last, what about the electron spin quantum number, or this is the symbol EMS, representing the spin. It specifies the way the electron spins or rotates, either counterclockwise or clockwise, or its axis as it moves within the orbital. It takes only 2 values. It may be a +1/2 or a -1/2. Again, the value of the EMS will be only for these 2, +1/2 and -1/2. Like this one, this shows that this spin is +1/2 counterclockwise. And then for this, -1/2 for clockwise. The arrows up and down can also be used to express the spin of the electrons. The arrow up signifies a counterclockwise, like in the Hunt's row, and of course the other one, arrow down, is for the clockwise. So if we're going to detect the spin of the electron in hydrogen, it's counterclockwise. In helium, you will see they are paired, diamagnetic, and in lithium, paramagnetic. And there is one here without any pair. So again, as a review, for the N, which is the principal quantum number, it tells something about the size of the orbit, or the distance of the orbital from the nucleus. For the azimuthal, that's the angular, or depending on the shape of the orbital, SPDF. Then for the magnetic, it's the orientation. And for the spin, with only two values, positive 1/2 and negative 1/2, it tells something about the electron spin. What about the rules that we need to follow in terms of these quantum numbers? Number 1, remember this. The three quantum numbers, the n, which is the principal, the azimuthal, which is the L, and the magnetic, that describe an orbital, are integers. So the value 0, 1, 2, 3, and so on. Next, the principal quantum number, or n, cannot be 0. Remember that. There is no element without any electron in their atom. It will always start in 1, and that is hydrogen. The allowed values of n are therefore 1, 2, 3, 4, and so on. All of them are positive. Because there's no negative orbital. Always remember that. Third, the angular quantum number, this one, the azimuthal, can only be any integer between 0 and negative 1. If n is equals to 3, for example, L can be either 0, 1, or 2. I hope that's clear. Not more than 3. Should be less than 3. And the fourth, the magnetic quantum number, this one, can be any integer between negative 1 and positive 1. If L, or azimuthal, is equals to 2, M can be either negative 2, negative 1, 0, positive 1, or positive 2. It should not be greater than 2. Fifth, when it comes to the spin quantum number, the symbol is MS, can only be positive 1/2 or negative 1/2. No other values are accepted. So therefore, if we have 2 as the value of the principal quantum, the possible azimuthal is 0 and magnetic is also 0. If we are going to somehow use the rules regarding this, and look at this. If n is 2 again, L can be positive 1. Lower than positive 1 can be 0, right? Or negative 1. Like this in my example. So therefore, I hope you learned something from this. The quantum numbers. See you again next review. Bye-bye.